Welcome to the third video on sequences and series out of 4. In this video, we'll cover arithmetic sequences and series. So what does arithmetic mean? In general terms, I like to think of it as a sequence or series that's evenly spaced or increasing or decreasing at a constant rate. I'll give you an example or two. By the way, this term arithmetic can be applied to either sequences or series. Here's a sequence, and notice that this sequence has a particular pattern. I'll pause while you notice it. You probably notice that this sequence is increasing by 4 each term. In the language of sequences and series, particularly arithmetic ones, we say that this has a common difference of 4, because the difference between any of the two terms adjacent to each other is 4. We also say that D equals 4 because in arithmetic sequence and series language, the letter D represents the common difference. Here's a series. You'll notice there's a pattern to this series as well. I'll pause while you notice the pattern. You may or may not have noticed that this series has terms that are decreasing. Each one is 7 lower than the previous one. So we could say it's decreasing by 7. We could also say it has a common difference of -7 because the terms are getting smaller. Or to use the formal language, D equals -7. We could also, by the way, write the series this way without the parentheses and the redundancy appearance of the plus next to the minus. Here's another sequence. You'll notice that this sequence is decreasing by 2 each time. We could say it decreasing by 2, or a common difference of -2, or D equals -2. And one more series. Notice this series is increasing by 2 as we go from term to term, and so we could say it has a common difference or a D value of 2. Here's a general formula that you can use for arithmetic sequences and series to either find a specific term or a general term. Let's look at an example of finding a specific term first. Suppose we wanted to find the 10th term of the sequence above. Well, I could use this formula. First, let's note some elements of the formula. It lists the first term in there, which we know is 7 by looking at the sequence. And it also has a D, or common difference, in the formula. And looking at the sequence here, you probably notice that the terms are getting larger by 4, and therefore we have a common difference of 4. So in order to find the 10th term, I can take this generic formula, and in place of the letter N, which represents the term number, I can put a 10. Good start. But I can also plug in the specific values of A1 and D that I know for this problem. And after plugging all that information, I can use the order of operations, simplify this, and find the 10th term. 10 minus 1 is 9. 9 times 4 is 36. And the final result, 43. By the way, it's probably worth noting that I didn't have to use this formula to find the 10th term. Watch this. If I had just taken the sequence and literally written out 10 terms, I would have found the 10th term that way. No reason you have to use a formula, but it's nice to know that you have the option. Let's now take that same sequence, but instead of finding the 10th term specifically, let's find the general term. Now in doing so, I'm going to take my same formula for arithmetic sequences and series, and this time, where the n's are, I'm not going to plug in anything specific, because I'm trying to find the general term, which is going to be a formula as a function of n. So I want to keep n as n, because I'm not finding a specific term. I still, however, know for this particular sequence the values of a1 and d, so plugging in the first term and the common difference, I now have an expression that will lead me to a simplified general term. All I have to do now is use some algebra to simplify it, distribute the 4, combine like terms, and I now have a good expression for the general term of this sequence. Now, even though I'm done finding the general term, it wouldn't hurt to remind ourselves what that actually means. To say that the general term is 4n plus 3 means that I could use that formula to find any specific term. Remember finding the 10th term earlier? If I had found the general term first, I could have plugged in 10 for n and done the algebra and found out what we already found out, which is that the 10th term is 43. So now, you may recall from an earlier video in this series that I promised you an algebra strategy to find the general term. I'll fulfill that promise now by bringing back this example from a previous video. In a previous video, we had this sequence of numbers, 4, 7, 10, 13, and so on, and our goal was to find a general term. And at the time, I said that a general term is going to be an algebra formula that brings me from 1 to 4. That same formula will convert 2 into 7, 3 into 10, 4 into 13, and so on. And at the time, I magically came up with the rule being times 3 and adding 1, and expressed the general term as 3k plus 1 as a result. Now, let's look at an algebra strategy that will avoid the guess and check element, the sort of trial and error algebraic cleverness element that we used in the previous video. So first, let's list the sequence this way, just for familiarity's sake. It's worth noting that a sequence can be listed in column form with the k values next to it, or in horizontal form but with commas between them. It still represents the same sequence. So now, notice in this sequence that our first term is 4, and notice that the terms are increasing by 3 each time. So what I can do is I can take this formula and I can take the letter n and switch it out for k if I like. By the way, there's nothing specific about what letter goes there. It's the exact same formula, whether I call that n or k or j or any other letter I want to pick. I'm only using k in this case because that's the one we used in the previous video. And now what I can do is notice that I know A1 and I know D for this particular sequence. I can plug in A1 and D in their respective places, leaving K alone, of course, because it's a general term I'm after. Distribute the 3, combine like terms, and I've got myself a general term, matching the problem from the previous video. Of course, this raises an interesting question. Will this algebra strategy, will the use of this formula always give me the general term? Well, yes, as long as the sequence is arithmetic. It's worth noting, however, that not all sequences are arithmetic. But if you're dealing with one, then yes, you can always use this strategy to find the general term. I think an important lesson in the world of arithmetic sequences and series is that not every problem It's based on a specific procedure like the last few. Here's an example of a problem that's non-typical, but we can still use formulas to find it. I'll pause while you read the question. Sometimes what I like to do for arithmetic sequences and series is write out blank spaces to represent the terms. Because I find that if I can visualize things, I have a better chance than if I'm using algebra alone. So they told me that the fourth term here is 10, and they told me that the eighth term is 16. Now I'm trying to find the 100th term. So my general strategy is to take my formula for arithmetic sequences and series and to plug in 100 for n. That's of course a logical thing to do if we want the 100th term. But notice, it would be really helpful if I knew a1, the first term, which I currently don't. It would also be helpful if I knew the value of d, which I really don't either. Perhaps I could discern d by the spacing of the fourth and eighth term. So I'm going to show you a couple different ways that you could go about finding d in this case. The first one is the following observation. This sequence increases by 6 in the space of 4 terms. Therefore, it must be increasing by 6/4, or 1.5, each term. You don't have to think of it exactly like I do. Some guess and check would just lead you to d being 1.5 if that's the way your brain works. But if that doesn't work for you, let me provide an alternative way you might find d in this case. So if we said to ourselves, well, I don't know what d is, but I know that this term is 10, so the term right after it must be d more than that, or 10 plus d. Pretending for a moment that we don't know that d is 1.5. But the term after that has to be d more than that, or 10 plus d plus d, also known as 10 plus 2d. And by the same logic, this term must be 10 plus 3d, and this term must be 10 plus 4d. But we know that that term is 16. Well, if the eighth term is 16, but the eighth term is also 10 plus 4d, there can only be one eighth term. Therefore, those two quantities must be equal. And I could then use basic algebra to find the value of d. I've shown you two ways to find d. There's other ways to go about it as well. But that's my conclusion so far. But I still don't know a1. That would be a helpful thing to know for this formula. Well, here's an idea. If d is 1.5, that means the terms are increasing by 1.5 at each step. But therefore, couldn't I take the 10 and work backwards by subtracting 1.5 repeatedly until I found out what the first term is? And that's precisely what I've done here. 10 minus 1.5, that minus 1.5, and that minus 1.5. And now I know the value of the first term of this sequence. Well, now that I've gone to all of the mental work of deducing the first term and the common difference, I can now plug those in and continue finding the 100th term. At this point, it's just a matter of order of operations. 100 minus 1, 99 times 1.5, and addition to get me to my 100th term. And while this was a pretty efficient way to do the problem, I just want to share an afterthought. Instead of going through all that, you could have written out 100 spaces. It didn't take me that long. And you could have said, well, there's my 100th term. Let's do this problem without any algebra whatsoever. I know the fourth term is 10 and the eighth term is 16, and that means every 4 terms I'm going up by 6. So 4 terms later I've gone up by 6. 4 terms after that I've gone up by 6. I'm not suggesting that this would be a typical way to solve the problem, but to be honest, this took me less time than the algebra method. Not all problems are doable and work out so nicely, but it's worth noting that you're never required to use algebra in a problem that you can solve without algebra. So now that we've been using this formula for a bit, it's worth asking, where did this formula come from? Let me take a few minutes to explain that. Before I do, it's worth noting that in most mathematics classes, you can use this formula without knowing where it came from. But I think it's worth knowing anyways. So let's take a brief look. Imagine that we had a sequence and we were looking at the first 6 terms. And imagine that we knew the first term, we knew the common difference, the spacing between terms, and let's say we wanted to know the 6th term. Wouldn't it stand to reason that to get the 6th term, we would have to take the first term, add d again, and again, and again, and again. The question now is, how many times do you have to add the common difference, d, to get from the first term to the 6th term? Well, the answer, of course, is 5 times, which can be represented algebraically this way. Read as the 6th term is equal to the first term plus 5 times the common difference. Imagine further that instead of wanting to know the 6th term, we wanted to know the 100th term. Well, if we wanted to know the 100th term, and we knew a1 and d, wouldn't we just keep adding d until we got out to the 100th term? The question then is, how many times would we have to add d? Well, if you think about it long enough, you'll realize you'd have to add it 99 times to get from the first term to the 100th term. In fact, I think it's fair to say in general that whatever term we want, we could add 1 less than that whatever number of d factors to the first term. Or to sound more algebraic, rather than using the word whatever, let's let n represent any particular term that we want. And what this shows is exactly where that formula came from. So far in this video, we've been talking about arithmetic sequences. Let's shift our attention now to an arithmetic series. You may recall that a series is just an addition problem of sorts, where the numbers in that addition problem form a predictable pattern. I'll pause while you notice the pattern in these numbers. You probably noticed that they're increasing by 3 each term. By the way, these 3 dots, or the so-called ellipsis, is worth noting here because it means that we're adding up all the numbers, including the ones in between 17 and 89 that follow this pattern that we didn't list. So this is quite a bit of numbers that we're adding up in this problem. Well, it turns out there's a great concept that we can use to find the sum of an arithmetic series. What you do is you take the number of terms and you multiply that by the average of all the terms, which in the case of an arithmetic series, an average is the first term plus the last term divided by 2. Because it turns out the average of all the terms, this is only true for arithmetic series, would be the same as the average of the first and last. Nonetheless, here's the concept that we have to use. I'm going to express this using algebraic symbols instead of words, but note that these two formulas mean the same thing. So n represents the number of terms, a1 represents the first term in our series, and an represents the last term in our series. Notice by looking at the series at the top of the page that 8 is the first term and 89 is the last term. So I can plug in 8 and 89 into this formula. So far, so good. That's the easy part. The challenge now is to find the number of terms in this series. Well, there's multiple ways one could go about this. Look up at the series. One thing you could do is just count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, and you'd have to count all the ones in between all the way out to 89. You may even have to write them all out. But it wouldn't take you forever. You certainly could write them all out and then count them. And that would be n. And then we could finish this formula. However, I'd like to provide you with a more sophisticated algebraic way of going about this, rather than manually counting them. What we could do is we could take our series and think of it as a sequence. Notice the plus signs I've changed into commas. This doesn't really change anything, just our mental perspective. So now just think of this as a sequence, and we want to know how many numbers are in it. Well, again, we could count them manually, but that would be a lot of work. So instead, let me utilize the general term as a means for counting how many numbers are in this sequence. Watch how I do that. As we know, this is the generic formula for general term. In our particular case, A1 is 8 and D is 3. You'll notice the common difference of 3 here. And just doing a little bit of algebra, I now have the general term. But here's a cool trick. I don't know what n is, but I do know what I want an to be. In other words, I can replace my last term with 89. By doing this, I'm setting up an equation where I can find out what value of n would lead to 89. In other words, which term number is the term whose value is 89. So if I just do the basic algebra here, 84 divided by 3 turns out to be 28. I don't want to go into algebraic detail, but it's a pretty simple equation. And what this means, n equals 28, is it means that the 89 in my sequence is the 28th term of that sequence. But remember, my sequence that I'm studying is really a series. Let me put the plus signs back. So equivalently, we can say that this series has 28 terms. And I've now utilized the general term to find the number of terms in this series. And I can now replace n with 28. And now I'm going to find the sum of the first 28 terms. At this point, the only thing left to do is the arithmetic. 8 plus 89, and then 28 times 97, and then dividing by 2 tells me that the sum of all these terms is 1,358. That's my final answer. By the way, it's worth noting that you could always check this on a calculator by literally typing in all the terms of the series, and you would indeed find that that sum is 1,358. And that concludes the third of this 4-video series.